Today we're going to continue our discussion of the atomic theory. As you recall, we have three models of the atom right now. We have the Dalton model, and Dalton thought that the atom was the smallest particle in nature. You couldn't get any smaller than that. There were no subatomic particles. This became known as the billiard ball model. And then we learned about J.J. Thomson, and we had the Thomson model of the atom. And remember, Thomson had this spherical idea with these positive particles in this atom, and embedded in that positive matrix were an equal number of electrons. This became known as the plum pudding model of the atom. And then we most recently learned about the Rutherford model of the atom. And Rutherford's was quite a bit different than Dalton and Thomas. We have this very, very tiny nucleus where the protons were all concentrated, and it didn't take up much space at all, but most of the mass was in this tiny nucleus, and huge distances away from this nucleus were these electrons that orbited the nucleus. So we're going to draw something like this. So we said that matter was mainly empty space because of the huge distances between the nuclei. This became known as the Rutherford planetary model of the atom. And that's where we are right now, and we're going to expand upon that in later discussions. But today, I want to talk a little bit about a third particle that Rutherford predicted existed. The mass of an atom was bigger than we could account for. So there must be a third particle, but it was very difficult to isolate. Rutherford predicted its existence. It wasn't until 1932 that this third subatomic particle was discovered. It has no charge, and it has about the same mass as a proton. These particles are known as neutrons, and their symbol is a lowercase n with an uppercase 0, symbolizing a neutron with no charge. Turns out that neutrons and protons are made up of even smaller particles. It's hard to imagine, isn't it? But it's well beyond the scope of this class. So the only subatomic particles you need to worry about for this class are protons, neutrons, and electrons. Now, while working with neon, J.J. Thomson observed that there were a couple of different kinds of neon atoms. They were exactly alike chemically, but they had a different mass. So they were the same chemically, but they had a slightly different weight to them. Atoms of the same element, but a different mass, are called isotopes. Isotopes have the same number of protons, and it turns out the same number of electrons. Remember, protons need to equal electrons to maintain the charge balance, but they have a different number of neutrons. So as a result, they'll have a different weight, but they'll behave chemically exactly like each other. And those are called isotopes. So let me give you a few examples. Let's talk first about the isotopes of hydrogen. I want to add another column here called electron, and then to the right I want to add another column called isotopic notation. Okay, so we're going to make this chart a little bit bigger than what I have in your notes. The first and by far the most common isotope of hydrogen has one proton and no neutrons. Now, by the way, since it has one proton, won't it also have one electron? Protons and electrons must equal each other in neutral atoms. Scientists have named this protium because it's essentially just a proton. Of course, there's an electron buzzing around it as well. Now, mass number, kiddos, is the sum of the protons and the neutrons. We don't worry about the electrons. Remember, it takes about 2,000 electrons to equal the mass of one proton or one neutron. So the mass number of an atom is accounted for by adding the protons and the neutrons together. So The isotope of protium has a mass number of 1 proton and 0 neutrons. A very, very rare isotope of hydrogen has been isolated, and it has 1 proton and 1 neutron. Now, by the way, it also has 1 electron. Now, its mass number, 1 proton plus 1 neutron, is 2. And finally, an even rarer isotope of hydrogen has 1 proton and 2 neutrons. Of course, it still has 1 electron. Remember, protons and electrons need to equal each other. So 1 proton and 2 neutrons gives it a mass number of 3. Now, this last column here is called isotopic notation. What it consists of is the symbol for the element, and in the bottom left-hand corner, we put the number of protons. So the number of protons goes right in the bottom left-hand corner. And in the upper left-hand corner, we put the mass number. And this is called isotopic notation. It shows us that the element is hydrogen, it has 1 proton, and its mass is 1. What would the isotopic notation for deuterium be? Well, it would still be hydrogen, wouldn't it? It would still have 1 proton, but its mass would be 2. And finally, tritium, hydrogen, and it would have 1 proton and a mass of 3. This is called isotopic notation. Now, when you look at the periodic table, you'll see the symbol for the element, and let's just pick on carbon for right now, right in the middle. And usually above that symbol is an integer, a whole number. For carbon, it is 6. That number represents the atomic number. The atomic number is the number of protons, kiddos. And it also, for a neutral atom, is the number of electrons. Beneath the element symbol usually is a fraction. For carbon, it's 12.011. This is called the average atomic mass. It is not the mass number. It is the average atomic mass. And we'll talk about what the term average means and why this number is not an integer. Why is it 12.011 instead of just 12? And we'll talk about that in a later video. Now that we know what isotopes are, I think we can look at some different elements and we can figure out how many protons, neutrons, and electrons they have with a little bit more information. So let's flip over to the next page and let's try a few problems associated with this new term, isotope. So, sodium. Sodium is atomic number 11. So if you look it up on the periodic table, it's atomic number 11. That means it has 11 protons. Now I want to add another column here, number of electrons. And wouldn't it also have 11 electrons? Now, how would I determine the number of neutrons for sodium if I knew the mass number was 23? Well, remember, the mass number is the protons plus the neutrons. True story? So protons plus neutrons equal 23. Well, if I have 11 protons, how many neutrons would I have to equal 23? You would be correct in saying 12. So what would the notation be for this isotope of sodium? Well, remember, the lower left-hand corner has the number of protons, which is 11. The upper left-hand corner has the mass number, which is 23. All right, let me do another one, and then I'll have you do one on your own, and we'll see how you do. Copper. If you look up copper on the periodic table, its atomic number is 29. That means it has 29 protons. It also has 29 electrons. Now, if I told you that this isotope of copper had 36 neutrons, what would its mass number be? Well, protons plus neutrons equal the mass number, so 29 plus 36 is equal to 65. So the mass number of this isotope of copper is 65. Its notation would be the number 29 in the lower left-hand corner. Remember, the number of protons go down there, kiddos. And the number 65 in the upper left-hand corner, the mass number. All right, how about carbon? This isotope of carbon has 6 protons. It has a mass number of 14. Can you fill in the number of electrons, the number of neutrons, and then can you give me the isotopic notation? I'll give you a few seconds. So pause the video, go for it, and then press play, and we'll see how you did. Okay, welcome back. If you said 6 electrons, give yourself a high five. Electrons and protons are the same. If the mass number is 14 and you have 6 protons, doesn't that mean you have 8 neutrons? Very good. And the isotopic notation, once you have the number 6 in the lower left-hand corner, the number of protons, and the number 14, the mass number in the upper left-hand corner. All right, that's great for now. You can see in the next video we're going to do a lot more practice. So stay tuned, we'll do more of these, and you will get really, really good at this. See you soon, kiddos. Bye-bye.